Thank you. Can you hear me?
Yeah, so we can hear and see your screen.
Okay, thank you. So hello everyone. Today I'm going to discuss our current results and studies about the vorticity dynamics of entrainment and detrainment phenomena at the turbulent and non-turbulent interface. This is a work we have been working along with my advisor, Professor Fadli Hussein, and his postdoc, Edgardo Garcia. So during this presentation, we were going to first understand what is entrainment. Then we are going to understand what is the turbulent and non-turbulent interface, also known as the TNTI. We will see that entrainment can be measured by using entrainment velocity, and entrainment velocity is a function of entropy. And we were going to also understand what is the interpretation of entropy, the physical interpretation of entropy. We will see that we use an idealized model um, to understand the vortex dynamics of the TNTI, the effect of fine-scale turbulence in this idealized model, and finally, we're going to have some remarks using a real DNS of a temporal jet to explain some insights about the turbulent and turbulent interface dynamics. So first, entrainment, there has been many uses for this mechanism. Also, this mechanism has other other meanings. And some people just capture the essence of entrainment as how you can capture flow outside your turbulent flow and capture inside your turbulent flow. But we go a little bit more deeper and we go a little bit more into the details of vorticity dynamics of this effect. So in our case, entrainment, we consider as the process by which non-vortical fluid becomes vortical through interaction with existing vortical regions. And the importance of this start with the physical interpretation of why a turbulent flow expands over space. A very classical flow is a plane jet. You can see that the plane jet starts very small in their thickness, and then it starts to spread. There has been some studies of understanding this. This is a sketch from a colleague showing that a part that the jet is being expanding by seeing how the velocity profile is expanding in space, there is some arrow showing that there is non-vortical fluid getting captured in the temporal jet. So the entrainment mechanism can be divided in two sub-mechanisms or two different phenomena. One is called engulfment. So engulfment, what it's doing, represented by these yellow arrows, is how structures inside the turbulent jet or inside the turbulent flow advex or capture non-vortical fluid into the vortical fluid. This is a large-scale motion. We are not so interested in this mechanism, but we are rather interested in the mechanism called nibbling. So nibbling is how at each point of the interface will move towards the non-vortical fluid, making that the turbulent region will be expanded. This is thanks to the presence of small scale vortices. So you can see here in the picture that the small scale vortices are the ones that are very close to the interface, and they're the ones that are going to increase or decrease as how fast this interface is growing towards the non-vertical region. In the bottom, we see after this process happening, how in time the interface will expect to expand. And now, to give more insights about entrainment and turbulent interface, here's the illustration of a temporal jet of Reynolds number of 3000, where we are identifying two surfaces. One are lambda 2 structures, just to show the small filaments from an already turbulent flow, and in the top, a surface in orange showing the interface. So how we identify the interface? There has been quite good discussion about how is the correct way to identify the interface. But I will say that the most consensus goes into understand the interface as a threshold you can put, because by the way, the turbulent and turbulent interface is not a physical thing that is in the flow. It's just an interpretation that we just select a threshold and we select a specific threshold, and that is our interface. That in our case depends on the entropy domain or the entropy field. Entropy is just simply the square of the vorticity magnitude over 2. It's really similar. Their dynamics are quite similar, but not that quite. I will explain why. And once you select a threshold based on your entropy field, you can now put your interface and mark where is vertical and where is non-vertical. So to get more insights of what is entropy, which is the principal or the key value and the key scalar quantity to understand entrainment, we use a very simple example that I'm pretty sure most of you will follow. This is the classic Lambda vortex. You can see their vorticity profile in the top, their corresponding velocity profile in the center, and there's something that we already know, and is that there is the conservative quantity called circulation. Circulation cannot be decreased or increased in time. Um, so in this particular solution of the Lambda vortex, we can clearly see that by using the area integral of vorticity profile of the Lambda vortex. We see that the Lambda vortex profile depends on time and viscosity, but once you do the area integral, you see that circulation is always constant. There is no change of circulation independently of time or viscosity. However, for entropy, it's different. For entropy, if you do the same exercise, computing the area integral, but of entropy, in an infinite domain, you will see that during time, the amount of the area integral of entropy changes. So entropy and how a certain finite amount of entropy change in time depends on the viscosity and also in time. And I will explain also a little bit more about that later. So to give a final explanation of what is entropy, I would like to discuss what kind of things are the most relevant physical analysis that we can capture in entropy. So for that, we can use the entropy transport equation, which tells you how entropy will increase or decrease pointwise, because remember, this is an scalar quantity. So we have production, which is really similar as the stretching term in the vorticity equation. So production is telling you that your entropy field can generate entropy or kill entropy in an inviscid way. Also, we have diffusion, which is the classical diffusion. We can have a very similar effect in temperature, or just vorticity magnitude is the same thing. And also, there's a third term which is very interesting called dissipation. There's some discussion about if we can call dissipation, because there is not a clear way that we can understand this as how entropy transported into heat, but we can say that due to viscosity, entropy is being killed. And we see that dissipation, as you can see in this curve, depends on the vorticity field, not on the entropy field. So where vorticity is changing their gradient at maximum is the same point of where you have maximum dissipation. While for diffusion, it depends of entropy. So you see that the maximum points of diffusion is not have nothing to do with the maximum points of the change of curvature of the vorticity, and therefore it only depends of entropy. So then how we can measure entrainment? So we can use in our advantage the definition of what is entropy. So once you identify your interface, the interface will move. And the velocity of this movement can be decomposed into further velocities. One velocity is the entrainment velocity, and the other one is the advection velocity. The advection velocity is the already known advection effect from the flow that will be just moving the interface without having any transport or vorticity dynamics. I mean, the interface will be moving anyway. But there will be some changes in the local field of entropy. And since the interface is based on a threshold, every time you track a new, you have the same threshold for a different time step, the interface will move. So the local changes of fluid particles and their entropy will give you what is this velocity. So to get that velocity is really simple. You get that vection, the left-hand side of the entropy transport equation, which is that vection terms. We separate the velocity into the two velocities. Since the interface is based on a constant threshold, it doesn't vary in time, so we can go this equation equal to 0. And therefore, we can put into the right-hand side the entropy equation, because in the right-hand side, there is the velocity due to entrainment, and that is same as the one that we understood for how entropy is going to change, and that's why we use the terms of the entropy equation. And we only having that the entrainment velocity depends on each of the terms of the entropy transport equation. And this can also be further decomposed in three velocities, depending of what is the physical phenomena that is making the entrainment velocity to increase or decrease. A very good way to understand what is entrainment velocity and what are the entropy dynamics is the Borger's vortex, where you can see that the Borger's vortex, which is usually explained by the equilibrium between diffusion and stretching, in entropy dynamics tells you that entropy is conserved in all the times because as the Borges vortex is being stretched and is producing entropy at the same time is being killed by destruction and also is being diffused. And if we measure the entrainment velocity at each point in the radial direction of the Borges vortex, we see that there is a perfect equilibrium between the entrainment velocity due to stretching, due to diffusion, and also due to destruction via viscous effects. It's important to say, coming back into the how we identify the entrainment velocity, and is that the entrainment velocity, as you can see here, depends on the gradient. And since you know that actually the gradient is pointing inside the interface, because inside the interface, when you have most of the entropy, we will see that the entrainment velocity, the more negative it is better, because when you have a negative entrainment velocity, it means that the vector is pointing outwards. So therefore, every time we see that, for example, in this case, that the entrainment velocity is negative, actually means that the interface is supposed to expand into the other direction. So continuing our discussion, and now we are focusing on understand what are the dynamics of the interface that increase or decrease entrainment. So for that, we have a temporal jet simulation, but in this case, is not as the one I showed before. In this case, it's temporal. This allows us to get rid of some spatial effects such as vortex pairing, some in real time effects of the Kelvin-Helmholtz instability, and we just focus on the local turbulence without being an isotropic turbulence. So you can see here in the right side of the slide that there is the entropy profile or the entropy field, and you see that there is a lot of concentration of very strong entropy next to the interface. That helps us to understand that there is something happening inside the interface that makes entrainment velocity to happen faster or slower. In the bottom left is the temporal jet viewed from the top, but colored by the entrainment velocity, where in this case, red means very low entrainment and blue means high entrainment. And you see that if we make some cuts, the entrainment velocity now in this case represented by this vector shows that there is some sudden jumps. And these jumps also are identified next to regions of vortical concentrations. So here, then we go a little bit further, identify some particular vortices using lambda 2. We identify some of the vortices that are next to the interface. Then we identify two thresholds because we also see that if you identify two thresholds for the interface and you get two lines, then you can see more clearly how is the transition between entropy, between high entropy to low entropy. For example, a thin interface between these two lines means that the diffusion is going to happen faster because the gradient of entropy is sharper, while a thicker interface is the opposite. So for the dipole, you see that in the case of the stretching, the dipole will stretch the shear that is next to the interface. This will enhance the amount of entrainment, as you can see here by diffusion, how diffusion is stronger in this region than in this region. And also you see how the structure of vorticity, of entropy happens in between the two vortices, where is the maximum straining. Also, we identify just one vortex and see what is the effect of this vortex in the interface. We see that the vortex is driven the interface down closer to the vertical region, and in this side is making it thicker, and this side is making it thinner. And similar as the dipole, we see that the vortex stretch on vorticity in the region where the interface is thinner, and also diffusion happens faster there. Also, the problem of stretching the shear field next to the interface is that since the gradients now are more sharper, of course, destruction of entropy also happens faster, and that's something that will impact the entropy and therefore entrainment velocity. So now that we identify some vortices in the real temporal jet, we came into an idealized model. We want to use the same shear flow we generate plus a superposition of a vortex, okay? This again is a Lamusin vortex. The other is the shear field I just showed before. And we also understand that apart from the entrainment velocity, there is a more simple way to understand entrainment, which is a little bit more clear, which is how much the entropy field expands in space. So if we track the area fraction between between two time steps, and see how the vortex is rolling up the interface, is moving all the vortical fluid, and measure how much area of vortical fluid over the total area is changing in time. We see that is linearly increasing. And this is something that we will explain in a little bit moment. So in order to understand which are the key factors or key characteristics that change the dynamics of entrainment, we found that one very important factor is called the relative angle alpha that you can see here. The relative angle alpha is the angle between the vorticity vector of the vortex and the vorticity vector of the shear field. That in this case, the shear field is constant and is in one direction, so there will be only one direction for the whole shear. And the angle in between two gives you completely different effects and different configurations in the flow. So we have four cases. We have a case in where it's perpendicular, a case where it's 45 degrees, an anti-parallel case, and a parallel case. So I will go into the key conclusions of each of the configurations. So for the perpendicular case or orthogonal case, is a very important situation because you can clearly see the effects of stretching, compaction, because stretching can only happen when vorticity vectors are orthogonal. And you can see that the region that has more entrainment by these top arrows is the region where you have much stretching, which is the region of generation of entropy. Now, something important that I would like to remark is that these arrows are measuring entrainment velocity only in these contours of entropy. For the contours of production, dissipation, and diffusion, the arrows represents the entrainment velocity due to that effect. So it's very interesting to see that even though the maximum effect of the final entrainment depends on the production of entropy, you see that the entrainment velocity due to production actually is not that high. And the reason is because stretching is not happening at the interface, because the interface is a region that is very close to zero vorticity. And to stretch, you need vorticity. So the stretching increases the local entropy in some regions, but not on the interface. However, since these regions are not increased, diffusion is increased, as you can see here, because now the gradient became sharper, and therefore the entrainment velocity due to diffusion, you can see that is quite high. And also, since you have sharper gradients, of course, you will expect the destruction also happens faster. A very important point that we would like to discuss also is that you can see that in production, there will be regions of destruction, implicit destruction of entropy. However, these regions does not survive in time because these are self-destructing, because as I told you just before, to stretch or compact entropy or vorticity, you already need more vorticity. And since you already destroy vorticity, so you don't have more vorticity to get destructed, and that's why after some time you will see most of it to be stretching. For the parallel case, I will say this is a more simple case, since all vorticity is in the same direction, so we only have a very slow diffusion effect. You see that the only thing interesting happening here is that the interface becoming thicker, and I told you before that a thicker interface means a very slow entrainment, and that's why you can see by the arrows. And also, a thicker interface means lower diffusion and lower destruction. For the antiparallel case, we see a very interesting point, which is that since it's antiparallel, we are going from a positive vorticity, in this case is positive omega x, into negative omega x. And in between this transition, there has to be a region that has zero vorticity, as you can see by this white ring over there. That longer in time, this ring, after being distorted by the shear flow and gets this shape, is closer to the interface. And something interesting happens here, and it's that if you can see this part of the bottom left figure, there is a very clear sense of detrainment. Detrainment we interpret as how the interface, instead of going into the non-vertical direction, the interface actually will move towards the vertical region. And you see that it's quite high. The reason is because there is a cross diffusion process where diffusion is also being happening in one side of the interface and also in the other side of the interface. However, if this part of the interface has lower entropy, the interface will prefer to move into this direction. That's what is happening here. It's quite high. Um, you can see also that by diffusion, that exactly in that point, diffusion is very strong, similar dissipation. And finally, we have the most interesting case, which is the 45 degrees case. The 45 degrees case is a very interesting situation in where the vortex is placed in a exactly position where you can add together or superimpose the effects of the classical diffusion of the normal parallel case plus the orthogonal case. So you see that, of course, comparing to the other orthogonal case is not that high, the compaction stretching. However, since the vortex is moving to the right, you can see that now you have more available vorticity. And therefore, that's why you see that in the previous case, destruction of entropy by compaction disappears, but in this case, it just becomes stronger and stronger. And if you double check the arrows representing the net entrainment velocity, you see that there is a region of high detrainment in this region, and no matter which threshold you choose, this is always going to detrain. So that's why when we go into the temporal jet, we saw very clearly that there is certain regions with high detrainment or very low entrainment. That also happens to be similar as what we find here. In addition to that, we see that very close to a very intense detrainment region, we have a very intense entrainment region. And this sudden transition happens because at the same time you have a compaction, there is a generation of an internal shear layer which is going to be very close to the interface and will enhance the process of diffusion, as you can see here. So now you have a region of very high entrainment close to a region of very low entrainment. And to have a more qualitative understanding of this effect, this is a very simple sketch showing that you have the entropy destruction region that is compacting entropy, destructing entropy all the time. This will result always in detrainment. However, there is a generation of a shear layer because as the interface is turning to this direction, the vorticity vectors are tilting and are being intensified by the velocity gradient of the vortex, making a very strong shear layer, enhancing the process of entrainment. So to have a final conclusion into these different cases, we have three different mechanisms of detrainment, which makes the interface to go towards the vertical region. We have a first mechanism coming from compaction of vorticity. So you can see these dash arrows representing the velocity and seeing that this has a negative gradient. You see that is opposite to the direction of vorticity, and therefore the vorticity vector are going to be compacted. And therefore, since they are compacted, they decrease their magnitude in that direction, meaning that now the interface, as you can see here, from time 0 to time 1 is now moving into an arrows that are shorter because that's the constant threshold we just set. The second case of detrainment is wherever you have gradients of vorticity, that is always, you always going to have destruction of vorticity by viscosity if you have gradients of vorticity. So this destruction of vorticity or entropy by viscosity will just equally decrease the magnitude of vorticity. And since you decrease the magnitude of vorticity, so your interface is now moving downwards. And finally, the last one is the cross diffusion one, representing the 180 degrees case, in which now the interface moves toward a region that has lower vorticity. As you can see here, it moves down and then the interface moves in the other direction. Now we increase a little bit the complexity of the problem. We add fine scale turbulence. And we find first that the small scale turbulence here, showed by these lambda 2 structures, are now under shear that we just set. And we see that it gets this shape. This is because the shear gets perturbed the small scale fluctuations and small scale vortices and gave this shape. But you see that in the top, the interface has some enhancement of entrainment velocity colored by these red regions. And it's because outside the vortex, there is an azimuthal stretching of the fine scale turbulence that makes longer vortices, as you can see here, that increases the entrainment velocity. To have a more clear sense of that, let me show you this video showing what is happening here. So you can see that the vortices start having this region of negative, that in this case, negative mean detrainment, similar as the 45 degrees case, because we said 45 degrees case superimposed with fine scale turbulence, we see again the same detrainment effect, meaning that for the global geometrical aspects, the fine scale turbulence doesn't have any change in the final result. And if we keep going, we see also the jump of the high speed shear layer that increase entrainment. And finally, once the vortex in this capture is not seen here, generates a secondary vortex from the roll-up of the initial shear layer. If you can see here, I use the shear decomposition to identify shear to identify internal shear layer. So now that we take out the interface, we can clearly see here in green, using the shear decomposition, how shear can very useful to identify internal shear layers. And this internal shear layer that I just showed in the previous case, longer converts into a vortex because it's rolled up into a new formation. So you can see here that it forms a new vortex here. And between the first vortex and the second vortex, of course, there is a very intense region of this green, which represents shear. So then let me summarize the effects of the different angles for the fine scale turbulence. For the parallel anti-parallel case, we see that there is no big impact. Actually, you see that the entrainment velocity is exactly the same as with the fine scale turbulence. However, when you have a stretching and compaction, we see some laminarization region due to the compaction of entropy that kills the small scale fluctuations, and also the classic enhancement due to a stretching and generation of vorticity, and also the generation of the internal shear layer that later on roll ups into a new vortex. Finally, to get insight if whatever we identified in the idealized cases are correct, we use the temporal jet to get some data and some statistics about the interface. So here you see the temporal jet, white are lambda 2 structures, yellow is the interface, and we measure some quantities. For example, we see that the direction of where the interface is facing, supposing that we have an angle between the normal vector of the interface and the horizontal streamwise direction, angle theta, we see that is a preferred direction of where the interface is going. Also, we see that if we measure the curvature of the interface, we see that we have more concave style regions, as you can see here by the PDF, are now more interesting for our topic about vorticity and vortex dynamics. We see that the circulation of vortices next to the interface is actually higher, closer to the interface than away from the interface. To get this, what we did was that we used an algorithm that we individually take all lambda 2 closer 3D contours. We measure the circulation at the center or the most intense lambda 2 structure is. Then we measure circulation, and that's where we get the data. Similarly, we do the same thing by the shape of the vortex. We also find that the shape of the vortex getting close to the interface are actually bigger in comparison to where the size of the vortex are away from the interface. This also was using the same algorithm. And finally, our last work or the things that we're working in is that we see that there is large scale motion that is making, as you can see here in the temporal jet, in this case, we push a little bit more and we push into 10,000 Reynolds number, the temporal jet. And we see that there is some regions, which is red and blue, representing streamwise velocity fluctuations, showing that you can have in the streamwise direction high speed and low speed regions. And we see that in the high speed regions, there is concentration of fine scale turbulence. And we see that also, if we go a little bit closer and see what's happening, the presence of vortices are only in the high-speed region. And the reason is because the high-speed region represents the high-speed flow that was from the temporal jet that is going towards the non-vortical fluid, and the low-speed regions represents the advection of low-speed velocity fluid that is coming into the jet. So we measure the PDFs of the entrainment velocity, the net entrainment velocity, the entrainment velocity due to production, due to destruction, and to the diffusion. We see, surprisingly, that even though we have fine scale turbulence, we got higher values of entrainment velocity for the low speed regions, presumably because those are regions where the interface is very contortionate and there is highly jumps of entrainment from the presence of vortices, and therefore we found that to be quite interesting. So the conclusions of this study, we can say that the steady state of the Borger vortex can now be explained through the entropy balance equation. We see that our idealized model successfully reproduced the essential dynamics of vortices interacting with the turbulent and turbulent interface. We saw that detrainment is not threshold independent phenomena. I would like to make a point about this, and is that detrainment, usually people say, no, you get detrainment because you have your threshold really close to the vertical region, so you have compaction and therefore you will have detrainment. But we see that our idealized model shows us that there are some regions where detrainment always happened. Then we see that there is three primary detrainment mechanisms. One is inviscid destruction, other is viscous destruction, and other is the cross diffusion that I will just show in the last case. We see also that regions of detrainment and weak entrainment are preferably located in the highly curved regions of the interface showed by our visualization. And finally, we see that high-speed regions enhance the local entropy transport into the non-vertical region. So that's my presentation. Thank you for your attention.